Okay, thank you very much, Theo, and thank you all for being here. And in this presentation, I am going to discuss a practical situation, which is actually hard disk drive, and in particular, the technology of heat-assisted magnetic recording, which is actually coming on the market right now. This technology has been developed in the past 15 years, and very recently Seagate succeeded actually to really improve the performance of heat-assisted magnetic recording to the point that it can be launched on the market. So why I'm going to talk about heat-assisted magnetic recording? Because I will show that thanks to the combination of very local heating with a plasmonic antenna and combined with the motion of the media in a hard disk drive, it's possible to induce ultra-fast cooling of the magnetization. And in the media in which we are writing the information, and we can thereby create very strong thermal gradient in the media up to values like 100 Kelvin per nanometer, which is really a very, very huge thermal gradient. And I will show that these thermal gradients can induce actually spin currents in the media and induce an effective coupling between the grains in the media during the recording. And this coupling actually have consequences on the recording performance. So somehow, I will discuss ultra-fast phenomena, which takes place in a practical technology, which is this technology of heat-assisted magnetic recording. So for those who are not familiar with magnetic recording, I will start by introducing this technology. Then I will show that indeed we can get huge thermal gradients in the media, in the HAMR media. Then I will show how we can propose models for the resulting spin current and the thermal spin transfer torque, which are induced by these thermal gradients. And then I will show that experimentally we can determine the input parameter that we need next to perform micromagnetic simulations of the impact of this huge thermal gradient on recording performance. And then I will show that all this has an implication in the way we conceive the media on which we are going to write information. And then I will conclude. So let me start by introducing this technology of hard disk drives. So if you look inside a hard disk drive, this is what you are going to see. Usually there are several platters which are stacked on each other with two faces. And there is here a suspension with the write and read head, which is attached here at the end of this suspension, which can actually move across the disk to explore the whole area of the disk. And the disk itself are spinning at a velocity of about 7,000 revolutions per minute, which means a linear velocity of the order of 20 meters per second, so 20 nanometers per nanosecond. So we have here this media which is moving, and on top of this media, so flying above the media, we have the head here, and there are actually two parts in the head. One part is a writer. So the writer is a very tiny electromagnet which is providing a magnetic field which is used actually to switch the magnetization on the media. And so by using here the field underneath the pole of the head. And then behind this writer, we have a reader, which is a magnetic tunnel junction, which is used actually to read out the magnetic stray field coming from the media. So this is how we can write and read here in a media. And just to give a few numbers already, the fly height, meaning the distance between the head and the media, is nowadays of the order of 5 nanometers. And the bit size, the size of these bits here written on the media are of the order of 15 nanometers by 40 nanometers. For this density, which is nowadays in commercial products of 700 gigabit per square inch. So I like this slide from Jeff Childress. We used to work at HGST, part of Western Digital, but if we scale this a hard disk drive by a factor 1 million, the disk itself would have the diameter of the disk would have the size of the Bay Area in San Francisco, the San Francisco Bay Area. And actually, the head itself, the right-hand reader, would have the size of an airplane. And this airplane would fly at 5 millimeters above the ground. So extremely close at a speed of 12% of the speed of the light. And during this fly, actually, the head is able to seek, write, and read bits which have the size of a finger. So this is why this technology is really an amazing technology, and it's really something very amazing that with such dimensions and speed and constraint, the hard disk drive works. So in the past 60 years, tremendous progresses have been made in the areal density, in the density of information stored in a hard disk drive. And actually 10 to power 9 orders of magnitude in the areal density have been achieved since the first disk introduced by IBM, the RAMAC disk in 1956. In 2004, actually, we switched from longitudinal media to out-of-plane perpendicular magnetic recording, meaning that we are now using material which are magnetized out of plane. But this technology of perpendicular magnetic recording is reaching a limit. And due to this famous trilemma problem. What is this trilemma problem? The media which are being used in a hard disk drive are actually granular media, and for perpendicular recording, these are cobalt, chromium, platinum media consisting of grains separated by grain boundaries. And when we want to write a 0 or 1, basically, we set a bunch of grains in the up or down direction. And the boundary between bits, between 0 and 1 or 1 and 0, is not a straight line, actually. It follows the boundary of the grains. So if we want to maintain a sufficient signal-to-noise ratio in the media when we decrease the size of the grain, we have to keep the number of grains per bit constant of the order of 10 grains per bit nowadays. But we need to reduce the volume of the grain to actually reduce the size of the bits. So this means that to keep a sufficient signal-to-noise ratio, we need to keep approximately 10 grains per bit. So if we want to shrink the size of the bit, we need to shrink the size of each grain. But now we have this problem of thermal stability of the grains, because you know that in order to stay above the superparamagnetic limit, we need to fulfill this relationship where K is the anisotropy of the grain, V is the volume of the grain, and here we have the thermal activation energy. So if we reduce the volume of the grain, because we want to increase the areal density, we need to increase the anisotropy in order to maintain this relationship. But if we increase the anisotropy, now we have a problem of writability, because this electromagnet, the writer, which is a small electromagnet, can at most deliver a field of the order of 2 Tesla, and this is limited by the magnetization of the pole piece of this electromagnet. And nowadays we know with iron tantalum alloys and with nitrogen in it also to increase to reach a maximum magnetization of the order of 2.4 Tesla, but so the head can hardly produce more than 2 Tesla. So, and this field that we need to write is actually proportional to the anisotropy. So if we increase the anisotropy, we need to increase the write field, and somehow we are limited by the maximum field that the head can provide. So this is why this technology is nowadays reaching a limit, and somehow we need to do something about it to circumvent this trilemma. So we can do different things because this trilemma is based on various assumptions that we are using this continuous granular media, that the switching of the magnetization of the grains is macrospin, and that we write and store at the same temperature, and that we write with field only. But here we can do several things, and which have been actually investigated in recording industry. One way is actually to no longer use continuous granular media, but move to bit pattern media. In bit pattern media, actually, the material, the media itself, is nanostructured in the form of arrays of dots, and each dot carries one bit of information. So now you see that the separation between bits is defined by how we prepared these arrays of dots. And we no longer need to have 10 grains per bit here. We can have 1 grain. Each dot can be a single grain. And so as a result, we can actually use larger grains. And we no longer need to have something like 10 grains per bit. So as a result, even if we shrink the bits, we can have larger grains just because we have only 1 grain per bit instead of 10 grains per bit. Problem is that this is very costly to fabricate, and so industry actually, there is no way to produce this kind of technology in a competitive way. If we compare, for instance, with now a flash solid-state drive, which is more and more commonly used in industry, with the cost of flash memory going down. So this is actually working in a lab, and with very nice result, but it's not economically viable technology. Then there is another thing that we can do is actually to, instead of using only a hard material like a cobalt chromium platinum alloy as the media, is to couple actually on top of each other a soft magnetic material with a hard magnetic material. This is called exchange spring media. The idea is that the hard material provides the stability of the magnetization, but the soft material helps to nucleate the reversal of the magnetization, so that this allows to have simultaneously a good retention of the media together with a not so high switching field. And this is actually in use already in a perpendicular recording. Now we can also assist the writing by 2 different ways. We can assist the writing of the information, the switching of the magnetization by a temporary heating of the media. And this is what I'm going to explain in the following of the talk. The idea is to use high anisotropy material like iron platinum, which have very high anisotropy at room temperature. And then during write, we actually heat the media by a laser spot. I'm going to detail this, which actually reduces the anisotropy of the media. Then we can, with a weak field, switch the magnetization. And after switching, let the media cool down, and the large anisotropy is restored. So this is what I'm going to explain more. And then we can also assist the switching by a microwave. So this is also investigated in a recording industry. And the idea is that if we can generate locally a microwave on the media at a frequency close to the HAMR frequency of the media, then we can provide additional energy to the grains actually for their magnetization to switch in the field that the head can provide. So this is also an interesting technology under development. So let me now focus on this one. So why I focus on this one? Because in the roadmap from this consortium, Advanced Storage Technology Consortium here, HAMR is predicted as the next big technology. And Seagate is, as I said, is about to release products of this based on this heat-assisted technology. So how does it work? This is a sketch of how it works. So I explained that during write we need to heat the media to lower its anisotropy. And so this is done with, by focusing a laser on the media. And the media, as I said, is moving at 20 meters per second. But I will show that actually we want, because we need actually to write very small bits. And so we cannot just focus the laser on the media, because, you know, due to the diffraction limit here, the heated spot would be comparable to half of the wavelength. And in recording media, we want to write bits of the order of 20, 30 nanometer. So what we do is that we focus the laser on the plasmonic antenna, and this plasmonic antenna will emit a near-field electromagnetic wave, which is used actually to heat locally the media. So in this approach, we can use, as I said, much higher anisotropy material, and in particular iron platinum. And the media which are currently used in HAMR are iron platinum copper alloys with carbon grain boundaries. Iron platinum copper, why copper here? To lower the Curie temperature of iron platinum, because otherwise the Curie temperature would be in the range of 600 degrees C, and there is a lubricant on the surface of the so a polymer on the surface of the disc, which helps the sliding of the head, and this lubricant would not withstand such high temperature. So with copper, we can reduce the Curie temperature to around 400 degrees C, and so then the lubricant can withstand this kind of temperature. And also the heating that we need is thereby minimized. So the media actually looks like this. It's a granular media. So you see here these grains, and the size of the grains are typically in the range 6 to 8 nanometer. This is a distribution of grain size. And so we have here the magnetic media itself, this iron platinum copper carbon alloy. So the carbon is a segregant which diffuses to the grain boundary. And then we have a seed layer here, which is actually magnesium oxide. And then underneath, we have a heat sink. It's a copper-based alloys, which actually pump the heat, which will be dissipated here at the top surface of the disc. So as I said, since we want to heat locally, we cannot just focus the laser directly on the media. The laser is focused on a near-field transducer. This is a plasmonic antenna, so it's made of a cobalt-based alloy, because gold-based alloy, because gold is very good for plasmonic emission. And the size, so this the shape of this plasmonic antenna, well, this is from Seagate here. It has a lollipop type of shape, and at the end here of this plasmonic antenna, the size is 30 nanometer. So it allows to create a spot here of the order of 30 to 40 nanometer, a heated spot on the media of the order of 30 to 40 nanometer. So let me explain now that thanks to this local heating and the motion of the media, we can achieve very strong thermal gradients in the media. So first, a general consideration about the cooling rate in a metallic material as a function of the heated area. You know that the heating and cooling is described by this well-known equation of heat diffusion, where we have here the diffusivity of the media, which is given by this expression. This is here the source term. So in that case, it will be the plasmonic antenna. This is actually the density of the media and the specific heat of the media. So if you are interested in the cooling dynamics, when the media is moving underneath the plasmonic antenna, so the media is heating up when it passes just below the plasmonic antenna, and as soon as it moves away from the plasmonic antenna, it starts cooling down. So once it has passed on the other side of the plasmonic antenna, the source term here is equal to 0. So we have the time variation of the anisotropy, which is given basically by diffusivity times the Laplacian of the temperature field. So this can be approximated this way. And so the time for the cooling, we can have an idea of the time of the cooling as the ratio of the square of the heated size, so basically the heated area, divided by this diffusivity constant. So if we take a material like cobalt, we can, from this expression, calculate that if we heat 20 nanometer of cobalt, so a kind of hemisphere of 20 nanometer of cobalt at the surface of a bulk cobalt, then we will cool in 20 picoseconds. Now, if we heat 200 nanometer, so a hemisphere of 200 nanometer, this one will reach thermal equilibrium in 2 nanoseconds. So this shows that we can get ultra-fast cooling provided we heat a very small area. And this is why we use plasmonic antenna in this technology, because not only we want to heat a region comparable to the bit size, but also we want to cool very fast. So thanks to this, actually, it's possible to create a very strong gradient in the media. And these are actually simulations performed at Headway Technology using a finite element solver simulation of the profile of temperature underneath the heat spot. So you can imagine that the media is moving underneath the heating spot here, so the plasmonic antenna, at a velocity of 20 meters per second. So the horizontal scale can be viewed either as a snapshot of the temperature profile or as a time variation of temperature in a given grain. So a grain is warming up as it gets closer and closer to below the plasmonic antenna, and then after it cools down quite quickly. And you see that here the blue curve is actually the thermal gradient. We can achieve thermal gradient of the order of 7 Kelvin to 10 Kelvin per nanometer. And this is due to this combination of heating on length on a narrow length scale, together with also in terms of conductivity, the vertical conductivity in the media is much higher than the lateral conductivity. And the heating is very short, 2 nanoseconds, typically, which correspond actually to the motion underneath the plasmonic antenna, so of the order of 40 nanometer wide at a velocity of 20 meters per second.
So at the beginning of the talk, you actually gave a number more like 100K. Nanometer.
Yeah, but I'm coming to this because this is actually an average thermal gradient along the media. But in the future, actually, this is actually an expectation when the areal density will increase to 2 or 4 terabit per square inch. It is expected that the thermal gradient actually will have to be increased to 14 or 18 Kelvin per nanometer. But this is the longitudinal average thermal gradient. Now, if we look again at the structure of the media is composed of metallic grains surrounded by insulating grain boundaries. And because the thermal conductivity in the bulk of the grain is much higher than the thermal conductivity of the grain boundaries, the temperature along this bunch of grains here is a kind of step-like function. Most of the drop of temperature occurs across the grain boundary, not across the bulk of the grains. So it means that if we have an average slope of, let's say, 10 Kelvin per nanometer, if we assume the grains are 8 nanometer in diameter, it means that every time across the grain boundary, we have a temperature difference of 80 Kelvin. So it means that since the grain boundaries are 1 to 2 nanometer thick, that we can have a thermal gradient here. These steps here correspond to thermal gradients of the order of 80 Kelvin per nanometer. So it's really huge. You know, in the field of spin caloritronics, there has been several studies on magnetic tunnel junction and about the spin transfer torque and induced by difference of temperature between the electrodes. And this phenomenon was first predicted by Gerrit Bauer in 2007, that thermal gradient could create spin current and also thermal spin transfer torque. This was observed experimentally by various groups, as reported, for instance, in this paper, and in a magnetic tunnel junction. But here, people, and in particular in this study by Stuart Parkin, they use a heater actually to create a thermal gradient across a magnetic tunnel junction. And they claim that they observe giant thermal spin torque actually in this tunnel junction with a gradient of 1 Kelvin per nanometer. But you see that in our case, we have 80 Kelvin per nanometer, so almost 2 orders of magnitude larger than in these experiments on magnetic tunnel junction. Now, we can consider that 2 grains separated by a grain boundaries is similar to a magnetic tunnel junction. We have 2 magnetic electrodes with a tunnel barrier in between. So it's, we have the same physics than in magnetic tunnel junction with very large thermal gradient. And simply, so the physical principle is identical, but the geometry is different. So the conclusion is that we can expect quite significant spin caloritronics effect and thermal spin transfer torque taking place in the media in HAMR recording. So conclusion at this point is that we can expect this effect, and that this effect can impact the recording process during the cooling of the grains. And before explaining how we can model this effect, I'd like to give a physical picture. Yes?
Also during heating, right? Not just during the cooling.
Yes, but during heating, we are more or less erasing the information, but you are right, yeah, during the heating also. But the heating is actually erasing what was already written. And what matters in terms of recording is what happens during the cooling. But you are right that phenomena are also present during the heating. What can we expect? Let's suppose that we have that the plasmonic antenna is here, the media is moving this way, so we are in the cooling here process. And so during the writing of the information, so we are applying a magnetic field, let's say in the up direction during the cooling of the media. And let's suppose that we have here a grain which is still very close to the Curie temperature, like T Curie minus 30 Kelvin. And the next grain, the neighbor, which is cooler at T Curie minus 110 Kelvin. So here the anisotropy is already quite high in this grain, and we can consider that this grain is already frozen in the right field direction, that I assume in the up direction. Now, because this grain is hotter, it's emitting a lot of electrons, more than this one, and it's emitting both up and down electrons. But because this grain has up magnetization, you know, like in magnetic tunnel junction, if the magnetization is up here, this grain is going to emit, to transmit more up electrons than down electrons. So we are going to accumulate in this hot grain spin down electrons, which are going to favor anti-parallel orientation of the magnetization of this grain with respect to this one. This is basically what we expect, that during the cooling, the hot grain will tend to align anti-parallel to the already cooled grains. And of course, this is not good in terms of recording, because it means that if we want to write a 0 here, if this grain is already up, this one may orient in the wrong direction. So I'm going to show that indeed this is something which may happen and has to be taken care of. So let me now move to the modelization of this effect. And actually, we use the same formalism as with magnetic tunnel junction. So we consider here a tunnel barrier separating two magnetic electrodes. And in this magnetic electrode, we describe with this well-known band-splitted model of itinerant electron, which was first proposed by Maribeth Stearns in 1977. So actually, the formalism that we used is described in this paper here. I don't want to enter in too much detail at this point, but you see here the parameters that we used and to describe this system with a barrier relatively low, because we are using we want to describe these carbon grain boundaries, and carbon is a semiconductor with a relatively low barrier height. But we can calculate that with these values, actually, the spin polarization of the tunneling electron through the barrier would be 30%. And the area product, resistance area product of the grain boundaries would be 0.30 ohm micron square. And I'm going to show that experimentally, indeed, we are very close to this value. So by using Schrödinger equations and formalism described in the paper here, we can basically calculate the current flowing through the tunnel barrier as a function of voltage and difference of temperature between the two electrodes here. And so we obtain a two-dimensional surface here. And of course, in the media, there is no current flowing, no charge current flowing between the grains, because what happens is that there is a thermoelectric voltage which appears between the grain, which compensates the fact that one grain wants to emit more electrons than the others. So by setting the current to 0, we can determine the relationship between the thermoelectric voltage here and the difference of temperature between the neighboring grains. So for instance, 80 Kelvin would give something like 1 millivolt between the neighboring grains. Next, we can calculate with the formalism the in-plane, the two components of the spin transfer torque, the in-plane, which has a damping-like form, like the usual spin transfer torque, so this form, which resembles Gilbert damping. And we can calculate the perpendicular torque, which resembles the precessional Fick-like term. And we know from spin transfer torque in perpendicular magnetic tunnel junction that actually this in-plane torque plays the main role in controlling the switching of the magnetization. This one changes the frequency of the precession during the switching, but does not change the critical condition which determines when the magnetization is switching. And so by using the relationship that we determine here between the voltage, the thermoelectric voltage and the difference of temperature, we can actually extract the in-plane torque and the perpendicular torque as a function of the difference of temperature between grains. And so for 80 Kelvin, we would have this negative value here for the in-plane torque and this value for the perpendicular torque. We can also define a torquance, but this is defined as the ratio of the derivative of the in-plane and perpendicular torque with respect to the temperature. But at this point, I'd like to point out that the torques are the in-plane torque, the main one, is negative. This is what we see here. We have a negative for positive variation, plus 80 Kelvin difference. Here we have a negative torque. What means having a negative torque is actually we are using the same sign convention as in this paper, in which we calculated this torque in magnetic tunnel junction. And if we look at negative, so for a positive bias, if we have a positive bias here, electrons are actually tunneling from free to pin layer. And we know that in magnetic tunnel junction, if the electrons are tunneling from free to pin layer, this favors anti-parallel alignment. and this corresponded here, positive bias, to negative torques. And so it means that negative torque corresponds to favoring antiparallel alignment. So this is what I explained. We found here negative torques, and so negative torque indeed favors antiparallel alignment between the hot grain and the already cool grain. So now there was a very important parameter in this theory, which is the polarization of the electrons tunneling through the grain boundary. And I am going to explain now how experimentally we have determined the polarization of the electrons tunneling through carbon in actual media. So the media that we investigated was deposited at NIMS in Tsukuba in Professor Ono's team by co-sputtering of iron, platinum, carbon. And so this is what the hysteresis loop looks like here with coercive field of the order of 4 Tesla. And this is the structure of the media. And here, since we afterwards, I am going to explain that we want to measure the transport property of this film when the current is flowing in plane in order to measure the tunnel magneto resistance through these grain boundaries. So we deposited this material directly on the magnesium oxide substrate to avoid shunting in any metallic underlayer. And so the sample, this media, has been patterned in the form of a metallic, of a stripe like this, with 4-point contacts. And we applied a voltage between the two external contacts and measured the current flowing through the device. So we inject current through the external contact and measure the voltage between the inner contacts. And we got this IV characteristics, so very linear. And so in terms of electrical transport, so the electrons are flowing in the plane of the recording layer. And basically, they are tunneling from one grain to the next through this carbon grain boundaries along the electrical field direction. So we can consider this recording medium as a number of tunnel junctions connected in series. And we have about 1.4 10 to exponent 5 magnetic tunnel junction connected in series. So from the measurement of the slope here, we can determine the resistance and the array resistance area product of these grain boundaries, and we got 0.28 ohm micron square. So it's not too different from the 0.30 ohm micron square that we had with the theoretical parameters that we determined. So besides this value, we want also to know the polarization of the electrons. So for this, we measured the magneto resistance of the media. So you see here the magneto resistance response of the media with this in-plane current, and it looks like a GMR, a current in-plane GMR or current in-plane TMR with maximum of resistance close to the coercive field. And this can be understood by the fact that at the coercive field, this is when you have maximum number of grains which are in antiparallel alignment. And on the contrary, at saturation, all grains are parallel. So this increase of resistance is really due to the to the change from parallel to antiparallel orientation of the grains. But now this TMR amplitude is not very large. We measured 0.23%, but we are interested in knowing the intrinsic magneto resistance of each junction. Here, this is a kind of effective magneto resistance of the media, but if we want to access to the magneto resistance of each individual tunnel junction, we need to know the proportion of grains which are in parallel or antiparallel alignment at the coercive field. So for this, we made MFM experiments, and you see that we see some domains here in the recording media at the coercive field, which means, and the size of these domains is typically of the order of 80 nanometer. So considering that the grain size is 8 nanometer, this means that in this domain we have typically 10 grains up and then 10 grains down and 10 grains up and so on. So only 1/10 of the grains are in antiparallel alignment. So it means that we have here, when we measure the TMR, a dilution effect. And if we correct from this dilution effect due to the fact that we have only 1/10 of the grains which are in antiparallel alignment, we can deduce that the intrinsic TMR of two neighboring grains in switching from parallel to antiparallel will be 2.3%. It's still not very high, but considering this expression of the TMR as a function of the polarization of the tunneling electrons, this means that the polarization of the tunneling electron is 11% here. In the theory, with the parameters that we choose, we determine 30% of spin polarization, and experimentally we found 11%, so 1/3 of the theoretical value. So this can be explained by the fact that the theory was developed at 0 Kelvin. Here we are working at room temperature, and we can have also a spin flip taking place in the grain boundaries, which can reduce this polarization of the tunneling electrons.
One question. So on top of that, I assume that you have also the possibility to go around. You don't need to go in a straight line, right? So if you had, in other words, if you only had 1 million tunnel junctions in series, you wouldn't see any conductance at all. So you have plenty of channels in parallel to go through, and then you can also look going in circles or something, right?
Yeah, you are right that locally the electrons can wander a little bit, but basically they can jump on this grain, then back on this one, and things like that. Yeah, you are right, but here we are really dealing with orders of magnitude. But you are right that you can have this wandering of the trajectory of the electrons here. But this would very slightly correct the values, but not the orders of magnitude that you are trying to determine here. The second thing that you have to take into account is the fact that during this phenomena here, we are not considering the magnetization at room temperature, but magnetization at 100 Kelvin below the Curie temperature typically. And if we look at this magnetization curve as a function of temperature for this iron platinum or iron platinum copper alloy, we see that already we see here the Curie temperature, but already 100 Kelvin below the Curie temperature, we already have something like 60% of the magnetization which has built up. So it means that, of course, we are not going. We don't have to consider the magnetization. We must not consider the magnetization at room temperature, but the magnetization at 100 Kelvin below TC. But this is 60% of the magnetization at room temperature. So it means that in the simulation that we are going to perform, we have to take this factor 3 here, plus the factor 60% here, if we want to really take the proper value of the spin transfer torque amplitude that we are going to plug in the micromagnetic simulation. So this means that if I look at these two factors, the actual spin transfer torque that we have to plug in the micromagnetic simulation is 22% of the spin transfer torque that we calculated in the previous part of the presentation. So now I am going to show the impact on the recording performance, which can be deduced from micromagnetic modeling. So micromagnetic modeling was performed by Dr. Mizuno at TDK Headway. So you see here a picture of the media. So it's described by an assembly of Voronoi cells. So the thermal profile actually was this one, calculated from COMSOL. And we assumed that we had a right field, anisotropy field of 8 Tesla at low temperature for this iron platinum type of media, and a thermal gradient of 6.5 Kelvin per nanometer. And here what we did was to vary the amplitude of the spin transfer torque, which was plugged here in the LLG equation. You see here the usual terms, and here the two terms due to the thermal spin transfer torque, with the prefactor being the amplitude that we calculated previously. But this amplitude we multiply by this factor, and I said that nowadays with the parameters that we determine, we are at about 22% of the amplitude calculated from our initial model. So we are somewhere around here. What you see, so this is without any thermal spin transfer torque in the media, so neglecting this effect. We see that with 25%, the transitions are not yet much perturbed. So the effect, this means that the effect is still not very important. But if we go to 50%, we see already a degradation of the bits. And if we go to 75%, the degradation is much more pronounced. And at 100%, we see that the degradation is really very strong. So actually, we can even calculate the signal-to-noise ratio in this calculation. So by analyzing here the noise and the signal coming out of this media, and we see that up to 50% of the thermal spin transfer torque amplitude that we calculated previously, we don't have much variation in the signal-to-noise ratio. And above, we have this strong degradation in the signal-to-noise ratio. So here we calculated for two kind of geometry of the media. One kind in which we assume actually this distribution of grain shape and size, and another kind where we assume that everything would be completely perfect. But you see there is little difference between the two situations. Now, something else that we investigated was the relative role of the two components of the spin transfer torque. So here, actually, we are in the same situation as here. So we assume 75% of the full amplitude is present, both for the in-plane and perpendicular component of the torque, and we see that the bits are really badly written. If we now assume that the in-plane torque is 0 and just keep the perpendicular torque, we see that there is little perturbation of the written pattern of bits. And on the contrary, if we assume that we have no perpendicular torque but an in-plane torque, we see that we have again a strong degradation of the bits, like here. So it means that as observed for out-of-plane magnetized STT-MRAM, it's really the in-plane torque, the damping-like torque, which is controlling the switching of the magnetization, both in magnetic tunnel junction and in the media. But what does this mean in terms of media design? You understand from these kind of simulations that this huge thermal gradient and the associated spin caloritronics effect have a detrimental impact on the recording performance, because it tends to induce this anti-parallel alignment between the grains that are just in the process of cooling and the one which are already cooled. So it means that somehow we need to limit the impact and do something on the media to limit the impact of this phenomenon. And so the general idea is that we need to reduce the thermoelectric spin current, which is tunneling across the grain boundary between the hot grain and the cold grain. So several things can be done concerning the media. One first thing is to increase the grain boundary resistance to the array product by using insulating material instead of semiconductor material, like silicon oxide, tantalum oxide, instead of carbon or this kind of elements. Problem is that people actually already switched from oxide to carbon because the growth of the grains and the cylindrical shape of the grains is much better with carbon than it is with this kind of oxide. So that's why people decided to move to carbon. But carbon has this drawback of having a lower array product and also higher thermal conductivity than this oxide. So in terms also of lateral heat diffusion, carbon is not as good as this kind of oxide. Something else which can be done actually is to try to reduce the spin polarization of the electrons tunneling through the grain boundaries. So this can be done by inducing spin flip in the grain boundaries. So here we can try to incorporate in the grain boundaries heavy metal elements like tantalum, platinum, tungsten, which have high spin orbit coupling. And, but these elements have to segregate to the grain boundary inside the grain boundary material to actually induce this spin flip at the grain boundary. And then something else which can be done is to include spin sink above and or below the recording layer. For instance, if we include a platinum layer, this platinum layer, which has a strong spin orbit, can actually pump out the spin accumulation which is built up in the hot grain during the cooling of the hot grain. So these are various things which can be tried, but the general idea is that nowadays we are still okay because the thermal gradients are not too high. I mean, of the order of 8 to 10 Kelvin per nanometer. But if we go as expected in the roadmap to 14 or 18 Kelvin per nanometer, we will reach this region where the impact of this phenomenon is really very serious in terms of signal-to-noise ratio. To conclude, ultrafast cooling realized in HAMR media by combining local DC heating provided by a plasmonic antenna with the media motion allows to create huge thermal gradients across the grain boundaries up to 100 Kelvin per nanometer. And as a result of this, despite the polarization of the tuning electron is not very high, 11%, the gradient is so high that we generate a quite significant thermal spin current across the grain boundary and also a thermal spin transfer torque. And this tends to induce antiparallel alignment between the already cooled grain and the grain which are still hot, close to the Curie temperature. And this phenomenon really has to be taken into account seriously in the design of the media. And several ways actually to improve the media has been proposed to reduce the impact of this phenomena. And with this, I'd like to thank you for your attention. Yeah.